and welcome to That's Absurd. Please elaborate the supposedly science and ostensibly comedy podcast. My name is Julian Huguet. I am 0.5 of the hosts of this show. I know, I went decimal.
Wow,
I went fractional.
Decimals. I mean, that makes the math easy. 0.5 also.
Let me, hold on. 0.5 plus 0.5. 1. Okay, good. Continue.
Check. I'm Trace Dominguez, the other host of this podcast, the other 0.5 of this percentage pie graph. And in this show, we answer absurd, silly, ridiculous, far-out questions, and we use our science communication knowledge. Julian and I have been science communicators for like 12 years or something. So
oh, don't say that.
We Google stuff good. That's our real job.
So good at Googling. Or I called somebody this week.
You journalismed again?
I journalismed.
I love
did.
Journalism.
The response was underwhelming, but we'll get to that.
Okay.
I know.
Got it.
I know.
So in each episode, we get questions from our audience members and we answer those silly questions. And we hope you enjoy it. So make sure you ask us a question. If you have one, it's down in the show notes, or you can go to our website, that'sabsurdshow.com/ask. You can come find us on social media and, send us messages there. We may respond to them and we may ask your question here on this podcast.
Right. So this week we've got 2 more listener questions. And Trace, you're up first. So what was your question this week?
My question this week was from Aaron. And Aaron asked, would it be possible to have a permanent solar eclipse?
Ooh, topical.
Yeah,
topical,
this episode
Aaron.
is airing on April 4th, and that is just a few days from the Great American Solar Total Eclipse that will stretch from Maine through Texas. I will be in Ohio by the time this airs, hoping that it's not cloudy.
So you're going to be in the path of totality?
I will be in the path of totality. If
so
you happen
cool.
to be in Findlay, Ohio, look me up and say hi.
Is it a total really solar eclipse or is it annular?
It's a total eclipse. It is the only one hitting the United States continentally till 2044, I think, is the next one. So this is not a once in a lifetime, mostly, but it is once in a generation, if you will.
That's pretty good.
It's a pretty big deal. And it's going to go
through a big swath.
Yeah, it's going to go through some pretty incredible places. I think there are major cities that will have it. They don't even have to go anywhere. They can just stay at home and it will go right through their major city, which is pretty cool. A lot of people going to Texas. Austin is in the path, not in totality, but very close, I think. Our hotel is in the path of totality, so we can just go to the parking lot, which is awesome. But we're going to try and get a little closer. We'll get like 4 minutes and 20 seconds of totality, which is a huge amount. I saw the Oregon eclipse. It went from Oregon down into the south, and that one was in 2017. We had 2 minutes of totality. It went by in a flash.
I remember that one. My friend went with her now husband, who was from Oregon, and he, at that occasion, busted out a ring, an engagement ring, that had like a dark stone, a light stone, and a dark stone, or it might be the other way around. So it was like an eclipse ring. And I'm like, wow, nobody's topping that. That's pretty freaking good.
Is amazing. Wow.
Yeah.
Jeez. That's cool. I hope they're going to this one as well then.
Maybe.
Texas is going to be really crazy. If you are going to go, if you live near the path of totality and you are listening to this only a few days from now, this will be one of the most incredible events that you would ever see. I highly recommend anybody go. Just be prepared for the traffic because you have to get into the path of totality. 99% does not matter. We're going to come back to that. You really have to get to 100.
Doesn't cut it.
Really.
Close only counts in horseshoes and hand grenades.
That's right. And in a solar eclipse that is a total solar eclipse, if you have 99% solar coverage, it looks like an overcast day. But if you have 100% coverage, it's twilight. It's like amazing. Anyway, we'll come back to that in a minute. I wanted to thank Aaron for his patience. Aaron asked this question in October of 2023, and I saw it, and I was like, well, I have to hold on to this until the eclipse in April.
Boy, good thing. Can you imagine if we missed it for the most recent coming eclipse, and it's like, gotta hang on to this question till 2045?
Oh, no.
Oh, sorry, Aaron. I didn't see it. I forgot.
I'm only planning 2 things ahead of time, that far ahead of time. Obviously, the 2044 to 45 eclipse that'll pass over the continental United States. And, of course, the opening of the Nickelodeon time capsule in 2046 from 1996 to 2046. So, of course. So, let's talk a bit about a permanent solar eclipse.
Okay.
Right? Like, Julian, tell me, do you think this is possible?
Okay. Here's what I'm thinking, right? So a solar eclipse, right, is when the moon is between us and the sun.
Correct. Yeah.
And it's just so happens that like the angular size of the moon in the sky is just about perfectly the same size as the sun.
Correct.
But I mentioned annular solar eclipses. We had an annular solar eclipse last year.
Yeah.
And that's where like the moon is a little farther from Earth in its orbit. And so it looks a little smaller, so it doesn't take up the full sun. So I'm thinking, and I'm sorry if I'm stealing any thunder, but I'm thinking.
I asked. Steal the thunder.
It would be possible to have something at like a Lagrange point between us and the sun.
Interesting.
But it would be so far away that our moon that we have would be much too small to permanently block out the sun. But you might have like an annular, like a Lord of the Rings looking ring up in the sky. It'd probably be a pretty fat ring of the sun peeking out around the moon.
Like a Homer Simpson donut.
Yeah. Burning donut. Ooh. Yeah, that is my knee-jerk reaction.
Honestly, it's a great knee-jerk reaction. I don't think you stole any thunder, but you did.
Okay, good.
I would say foreshadow. That's another Eclipse pun. You did foreshadow some things. So, for those who don't know, Julian, I think, explained it perfectly. A solar eclipse is when the moon gets between the sun and the earth. It can actually happen to any planet. Permanent solar eclipse would then mean that the sun is always being blocked, like all the time, by some object. And there's a lot of astrophysics to think about here. Everything in the solar system, everything in the universe is moving constantly. And we know a lot of the calculations in order to understand that motion, but it gets very complex to think about having something be permanent in that kind of environment. So when a planet orbits a star, that's just one of thousands of variables that you'd have to account for in order to get a permanent solar eclipse. So I just want to say to Aaron, firstly, just off the top, it's not going to happen really easily. And if it does happen, we are either in big trouble or we're in a really interesting solar environment that may actually exist. So I'm going to keep you kind of on the hook with that. So on Earth, we get solar eclipses because of a fluke. We get a total eclipse, as Julian mentioned, because the sun and the moon just happen to be in our sky about the same size. The sun is actually 400 times larger than our moon, but it's also about 400 times further away. So the moon blocks like 99.99% of light from the sun sometimes when it just happens to pass at the exact right spot. And then we see the corona of the sun. You can Google pictures of this. We'll put one on our Instagram as well of just the corona. It's incredible. That's the sun's outer atmosphere. But the reason it's so hard to see and why you need to block 99.99% of the surface of the sun is because the sun is super duper bright. Even if 1% of the sun is not blocked, that is brighter by far than anything else in the sky. The sun is just that bright. So the corona is like 100,000 times dimmer than the surface of the sun. So that's why we need an eclipse to see it.
You heard it here first, folks. The sun, really bright.
Super duper bright.
Super bright. I don't know if you've read that in your science books. They don't teach. Yeah.
Oh, yeah. Actually, as long as we're talking about that, make sure you get real eclipse classes. If you do want to look at the eclipse, you'll be able to see the total eclipse from anywhere. It just won't be total if you're not in the path of totality, which is to say the shadow of the moon. But you'll be able to see the eclipse on Monday, April 8th from anywhere in the country. It just won't look like anything without solar eclipse classes. Or two index cards, poke a hole in one and hold the other one so there's a shadow of that like pinhole on the other one, and you can see the eclipse that way.
Just so y'all know, don't look at it. Sunglasses aren't enough.
No.
So like when you're looking, I did research on this for when the annular solar eclipse happened last year, and you're looking for something that's labeled, it meets the requirements for ISO 12312-2.
12312-2. Huh.
Yeah. So that's when you're shopping for solar eclipse, hopefully you're not finding some shady like retailer that just stamps that on there, but it doesn't meet those requirements. But yeah, ISO 12312-2. And if you get glasses like that, a lot of times they'll have like NASA stamped on the side or whatever.
Oh yeah,
but
you have some. Cool.
Yeah, but NASA doesn't like approve glasses that are put up for private sale, No. So don't fall for marketing gimmicks. They're like a government agency and they don't like getting involved in that sort of thing.
That's right. back to Aaron's question. So the reason, even though 1% of the sun is visible, it doesn't really look that much darker to humans is because of the way our eyes work. And I wanted to talk about this, a little bit of a sidebar. When you are standing outside of the shadow of the moon during a total eclipse, the eclipse doesn't look that different. It looks like, as I mentioned earlier, sort of like a cloudy day. And the reason it doesn't look that different is because, again, the sun is so bright, but also our eyeballs work really funny when it comes to how we perceive light. Researchers Weber and Fechner coined the term psychophysics, which is how we perceive physics, which also sounds like a term from like a sci-fi movie.
Ooh, I know we have a running joke of great band name, but psychophysics?
What kind of a band is psychophysics? I feel like there's a lot of electronic in there.
Acid rock, for sure. Psychophysics. Oh, anyway, man.
Amazing. Yeah, it's a term from the 19th century about how we perceive physics, like the human perception of the world. And they realized that humans perceive stimuli as in logarithmic ways, which is to say it's not a smooth curve, it's logarithmic, and if you double it, it like is an exponent instead. I think that's the easiest way to explain it, right?
Right. You need like 10 times more.
Yeah. Decibels are logarithmic. Yeah.
Hearing is a logarithmic scale, exactly, because like twice the loudness isn't like twice the decibels. It's like,
Yeah.
It's like 3 more decibels, basically. Yeah.
Yeah. It's like if you add 10 decibels, you're really making the intensity of the sound significantly larger. It's not a smooth line. It's a curved line, and it's very curved. So to put this in perspective, though, humans' perception to stimuli is logarithmic. So a coffee with 1 sugar versus 2 sugars in it, pretty easy to tell. Like we're like, oh, there's twice as much sugar, you know, but the difference of 50 sugars and 60 sugars is much harder to tell. We would just be like, oh, that's really, really sweet. It's still really, really sweet.
You need to go 50 to 100 in order to...
Yeah, exactly. If 50 to 100 would be a huge change, but we have trouble when things are we're bad at big things that make small changes. And so 1% versus 5% of sunlight, we might be able to tell, but 50% of sunlight versus 100% of sunlight, we almost have no perception of that. We cannot tell the difference between those two amounts of sunlight. That's not the physical reality of sunlight. That's not necessarily the sun is still sending us less light. We just don't perceive it that way. So interesting. So anyway, the math works out during an eclipse of something like 75% of solar coverage is a 4% drop in sky brightness.
Oh,
that's
okay.
Crazy, right?
Yeah.
So again, 75%. The sun is covered 3/4. Only a quarter of the sun is visible to us, but
just like a little dimmer.
Not that much dimmer.
No. Not
99% coverage of the sun, as I've mentioned, bright as a cloudy day, about 1,000 lux. That's still pretty bright. Like a cloudy day is still pretty bright out.
Right.
Even though 99% of the sun is covered. At 100% coverage, it drops precipitously and to like 5 lux.
Whoa.
Twilight. So you go from like civil twilight brightness to cloudy day. Well, the opposite of that. Cloudy day to civil twilight in like a minute.
That's
like
cool.
Seconds. That's why totality is so incredible. And outside of totality, it doesn't matter. It goes from being like a normal day to kind of a cloudy day, then back to a normal day again.
Yeah.
Like not a big deal. But if you're in that shadow of the moon called the path of totality, it goes from a super bright day to a cloudy day in about 45 minutes, and then cloudy day to civil twilight for 4.5 minutes, then back to a cloudy day in like seconds. And that it goes so fast, our human eyes cannot perceive the change quickly enough to see it happen. It's really incredible.
Path of Totality is Psychophysics' first album, by the way.
Oh, yes! My God. We need to make this band.
We should just make a band.
This is a good band. Like, wow. It's like Jethro Tull-esque, but with a fife. I can, we could do it.
I don't know. I think the band's already going to have the first fight, because the fife, it's always got to have a fife with you.
There's got to be a fife riff in there somewhere.
You got to have a fife solo. I've got a fever.
And the only prescription
is more fife.
Okay. So back to total eclipses that are permanent. So every planet-moon system is different. Our planet-moon system is actually really weird.
We have talked about this.
Yeah, I wrote, our moon is too big.
It is. Oh, wow, that's a deep cut. That's a deep internet cut. If you're
moon is too big.
If you're under 30, nobody's going to understand that. All right. But yeah, it is. I remember when we talked about when Ali Mateau was our guest, and he asked me about, like, what if the moon went away? And I did a lot of research. And yeah, I remember discovering that our moon, as moons go, is so large compared to the moons of other planets.
Yeah, it's really unusual. We have the largest moon relative to planet size that we know of. We're it. So it's like...
Now that Pluto's out of the club.
Yeah. Now that Pluto's not a planet no more. So... but, dwarf planets are different. So anyway...
Pluto's got a moon that's like 50% the size of Pluto, which is part of the reason they're
basically like co-orbiting.
Yeah, they're like, I don't know, who's orbiting whom at this point.
Right. So... Let me give you an example if you're not aware of all of the moons in our solar system, listener.
Are we going to count them all?
Let's count them. Ready? Enceladus, Iode, Ganymede.
Oh, that'd be such a good song.
That's going to be on our first album. Please buy Psychophysics' first album, Fathom Totality. So Mars has 2 moons, Phobos and Deimos, right? They're both super tiny and irregular, and there's no way that they could block 100% of the sun. However, and I will put this on our Instagram, Opportunity and Spirit in 2004 saw a Martian solar eclipse.
Oh, cool.
And they made a GIF of it. And then in 2022, Perseverance saw one, and they put a GIF of it as well. NASA made some. So we'll put it on our Instagram, but there's barely a drop in brightness when those moons pass because they're so small relative to the sun. It's just that fluke that our moon is so big and it just happens to be right in that path so it can block so much of the sun. Of course, if you were on Phobos or Deimos, would Mars block the sun? Yeah. So you'd get like a weird Mars eclipse and put the pin in that and keep it in your mind because that's where we're going to go a little bit.
Okay.
So obviously none of the gas giants have a moon big enough to block out the sun, and if they did, we'd be in big trouble.
Wait. I know there are some big gas giant moons, right? There's like Titan. It's named because it's so huge.
Yeah.
And it's bigger than our moon, and the sun's a lot farther away.
Right.
So are you saying that like it still wouldn't block out the sun? Or are you saying that like when we say total permanent solar eclipse, like the entire planet is shrouded in darkness? Is that what the question that we're answering?
That's a great point. So I thought about that when I saw Aaron's question. And as you know, right now, a total solar eclipse, which is when the moon blocks the sun on Earth, the shadow of the moon is quite small. I mean, it's big relative to a person, but relative to the planet, it's just like a little dot.
Yeah, it's a little like quarter-sized dot, yeah.
I think it's more fun to think about it in like a sci-fi way of like bathing the whole planet in shadow. However, even if you talk about like, yes, maybe there's a little teeny point, there might be an astrophysicist in the audience who can tell us that, yeah, Titan relative to where Jupiter is could cast a shadow. We know that moons cast shadows on planets. We have pictures of it. So if you want to talk about it that way, sure, absolutely. They could cause eclipses on their planets.
But like in a local sense, not like...
Right. What I'm talking about is basically a permanent eclipse, but that eclipse being so total that it covers the entirety of a planet.
Oh, okay. So you're going real big.
I'm like going even real big.
Even bigger than the solar eclipses that we have here on Earth. Like you're talking like Mr. Burns from The Simpsons sun shield plot.
Yeah. I think it'd be safe to say, we could mention it as a total eclipse being like our Earth or greater, right? Because Earth's is already pretty surprising relative to planets that we know of in terms of the size of our moon, the placement of it, the placement of the sun in the sky. Just getting that perfect coronal eclipse, we don't know if that could happen in a lot of places. So, and again, I didn't do the astrophysics math and say to every one of Jupiter's 700 moons. Not really. It's got so many
roughly.
Children. Yeah, it's like they find a new moon in Jupiter, and it's not even news anymore. NASA's like, we found another one, everybody.
Another basketful.
What's the internet gonna name this one?
Moony McMoonface.
Yeah, Moony McMoonface. So there are a lot of moons out there. Obviously, there's some big ones. But I think that's a great question, and it's important to remember. So there's no planet-moon system that we know of that would allow us to completely shroud a planet in their shadow. I mean, you could maybe argue like that a planet or a moon covers the sun as in it like transits across the sun really quick. But I think that's different than what the expectation here is from Aaron, which is a total eclipse like we see here on our planet. There are times when like Pluto's very far away. Perhaps there are times when, Charon covers the sun, right? Like blocks the sun for a bit while it passes. And is that a total eclipse? Yeah, maybe. Depends how you think about it.
Okay, but we want entire planet shrouded in darkness.
Yeah. And I think the key here, too, is...
permanent.
Right, it's not going anywhere. And I like that you bring it up because that's exactly where I was going next. So when we come to exoplanets, we start to look at these planetary systems outside of our solar system, which we discovered in the 1990s actually exist, although we theoretically knew there were planets elsewhere. And now we're sort of biased to finding really big planets that transit in front of their suns, as in, like, we can see them cross in front of the sun relative to our position, or we can see them pulling on their stars because they're so big. Yeah. So finding a teeny tiny planet like ours is really tough if it doesn't directly pass in front of the sun relative to how we're looking at that sun. And I say that sun, it's really that star. We just, colloquially call ours the sun. Right. I hope that's not confusing. But anyway.
Our sun is Sol, right? So I think so long as you don't call it a solar system, because that's technically, I've been corrected on that in the
interesting.
past.
So it would be like
you can call
stellar system? Would be more generic?
Yeah, star system. But I think you can still call it like its sun, right? Like the star that it is orbiting that's providing it light. I think that's acceptable.
Thank you for that.
Until somebody emails us and corrects us again.
Get in trouble again.
Which that's how we learn,
Please
okay? It's
email us. So, Aaron, do you want the whole planet to be in shadow? You didn't specify that in your question. But he did specify, I'm thinking about what it would be like for a moon to permanently block the sun, locked in, never ending. And so that makes me think, okay, it's going to bathe the whole planet in shadow. Aaron, do you want that?
Yeah, Aaron, who hurt you?
Imagine like a world in perpetual twilight. It'd be cold and awful. The oceans would freeze and plants would die and life wouldn't exist. It would go extinct because it'd be too cold. The sun gives us a lot of heat. And if we want a permanent spot on the earth, like if we did want that, I mean, we don't have a permanent one now, but almost every month or every other month somewhere on the earth, the moon casts a shadow, averages about 4 to 7 times a year. Sometimes it's over the ocean. So here's what I did. If we only want a spot, just a permanent spot, there's always a spot somewhere on the planet that has a shadow. It already happens 4 to 7 times a year. What if we just had like a couple more moons?
Oh, you're gonna up the moon count.
Up the moon count.
That's your plan.
So if it happens 4 to 7 times a year now, just like add a couple more moons, and then it will happen 12 to 21 times a year. That's like pretty constant. Not constant, not permanent, but like, pretty constant.
They're just tagging in all the time.
I did find a paper in Earth and Planetary Astrophysics that found the Earth could potentially support up to 3 Luna-sized moons, which is like moons our size. It could also, if we wanted more moons than that, 4 Pluto-mass moons or 7 Ceres-mass moons, which is pretty cool. Okay. So if we imagine they're spaced perfectly and this is a perfect universe, we could just triple the number of eclipses we get now.
Yeah, if they're smaller but closer, right?
Yeah, good point.
Then they'd be orbiting faster based on Kepler's laws of motion. Right. So they'd be like, you could have smaller, more of them then, like the Ceres size ones, and then on a lower orbit. Yeah. So then they're just they're rolling through.
Just eclipses all the time,
Yeah.
And so that's the most permanent physics eclipse that I could think of. If you are like, okay, it's just a dot on the Earth and it's just happening like at least once a month somewhere for, a couple days or a day or whatever, you get this like streak of a shadow crossing the Earth. That's about as permanent as we can get. However, if we ignore astrophysics entirely, Julian.
Oh, sure. Happy to.
No mentioning of Kepler's laws, no mentioning of any of the actual math, and instead do what I did and dig into the world of fantasy world building.
Okay.
So we try to design the perfect whole Earth bathed solar eclipse. Real physics be danged. So a permanent solar eclipse would only ever work if something was always in the same place in the sky relative to the planet, and it was always covering the sun, which would be really tough. As I mentioned, everything in space is moving all the time. However, Lagrange point 1 is in between us and the sun, right?
That's what I was thinking.
Every gravitational body has Lagrange points. Lagrange points there's several of them. James Webb Space Telescope is at Lagrange point 2. Lagrange point 1 would be between us and the sun. Kind of surrounding Earth, there are these gravitational, they call them parking spots. They're not actually static points, and they're not actually parking spots like you could just leave something there and they won't go anywhere without effort. They still need fuel to maintain that spot. It's just easier to be there because of gravitational forces kind of even out, you could say.
Yeah.
I don't really know how to describe them simply.
It's like the forces in that spot are kind of balanced to hold things there more easily.
Right. Yeah.
There's like 3 points in the same orbital plane as the Earth, and then there's like a point beyond the moon. But yeah, like you said, it's not perfect, and so that's why the James Webb's service life is limited.
Yeah, because it has to be expending fuel in order to stay in that spot.
To keep it there, exactly.
It's technically, in case you're not aware, it's at Lagrange point 2, which is, if you want to think the sun is in front of us, it is behind us. It's directly behind us then. So Lagrange point 1 would be in front of us on the other side of the moon's orbit, even further away. And Lagrange point 2 is behind us. And so it hangs out in our shadow behind us, which is why it works so good.
Yeah,
so
gotta get cold.
If we wanted a permanent solar eclipse, we'd need a really big thing in the way, likely at Lagrange point 1, to keep it there more easily, because we can't put it at the moon spot. This could happen in an exoplanet system like Cancri 55, where there are 4 large planets between 1 AU of the sun. So these like giant planets. If, for example, we were in a place like that, you would get, again, not permanent, but semi-permanent eclipses of these large planets blocking our view of the sun pretty regularly. You could have like a large gas giant close to the sun, called a hot Jupiter, with a rocky planet further out. There's no law that says inner planets are rocky, outer planets are gas giants. We have seen systems where there are rocky planets further away from the sun and still in a good spot for life, I guess.
Here's what I'm thinking, though, is that the Lagrange points exist where they are because it's like that balance of different gravitational forces, right? Like the Lagrange point between us and the sun is there because like the mass and the gravitational pull of the Earth makes that its parking spot. If you were to put like a gas giant that's more massive than the Earth in that spot, then that's not a Lagrange point anymore, right?
Yeah,
because
it would
like
move.
The Earth's gravity is not the dominant thing that's making that. Like we would now be basically the moon of the gas giant.
Well, no, if they were like orbiting, if you had a gas giant orbiting, say, where Venus was, there'd just be more mass, but in front of us, if you will. Again, if the sun is in front of us, right? So the Lagrange point would just move further away from us. There'd just be more mass. I don't know how much further. You'd have to do the math. But the orbit of Venus being closer to the sun also means that gas giant is going to go around the sun faster. Right. Kepler's third law.
How Venus
does. The square
does,
of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. I looked that one up.
I was going to say, do you have that on a tattoo somewhere?
No,
you just like ripped that one out.
I looked it up because I was like, I actually wanted to know if 2 planets in the same stellar system, look at that new vocab I worked in, could have the same orbital period. And the answer is not really.
Unless they were in the same orbital plane, or like distance from the sun.
Exactly.
Yeah.
And so you can't have a planet that's at Earth distance and a planet at Venus distance going the exact same speed. That was the first thing I looked up, because if so, we could have a permanent eclipse easily. Yeah. Because it would just be, they both, maybe it got hit by something and that's the orbit that it was able to maintain. But if it's going that fast, it's not going to be at that spot. It's just not going to happen. Kepler's third law just doesn't allow it.
It's just not how gravity works. It's why like satellites in low Earth orbit go around the Earth like 16 times a day. Yeah. But if you want a geosynchronous satellite that goes around the Earth once every 24 hours, it's got to be way farther away. And it's all Kepler's third law again.
Yeah. So just to kind of wrap it up here, there's really no way, Aaron, for this to occur. There are ways that we can make eclipses happen more often, again, adding more moons. There are ways that we could make those eclipses more dramatic by being, further out from a large planet that's in between us and our star. But all of this is unstable. So even if we were to take like full crazy sci-fi, okay? We have a geoengineering project. We built something that was tens of thousands of kilometers across, like 3 to 5 times larger than the moon. And we parked it at Lagrange point 1 in the solar system we currently have. It would bathe the whole Earth in shadow. However, keeping it there would be nearly impossible because L1 is an unstable location. So you'd have to really work on keeping it in that spot. And so permanent, no, unfortunately. If you could build a thing that was large enough, you'd have to be a civilization that could do almost anything from our perspective. So at that point, why are you doing that? What are you doing that for? You may as well just build a Dyson sphere and be done with it. So I hope that answers your question, Aaron. Unfortunately, no, we could not have a permanent solar eclipse. There's too many variables, too many things moving, and it's just not really a thing that we could do. That said, if, say, you're on If you're on Endor, they probably have a time of their year, potentially, where they're shrouded in darkness for a long period. Probably not that long, because the vegetation would die. And Endor is a vegetative, heavy planet. But any of these situations where there's a big object that can get between you and the sun, yeah, you'd have an eclipse for a while. Permanent, that's the word that we have trouble with when it comes to basically anything in space. Yeah, nothing's permanent, except for my love for you guys.
So it's a total eclipse of the heart?
Yes!
I was waiting to use it, and we had a chance. Yes!
Thank goodness. I'm so glad. I couldn't have teed you up any better, and I'm so glad
we got
you took
there.
it. With that, why don't we take a quick break so we can recover? Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
You know, we think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out.
Woo, welcome back to That's Absurd, Please Elaborate, a podcast where we answer silly questions. You already know that because you've been listening to it for about 30 minutes. Hello.
Unless you skipped halfway through, which is a brave choice.
Look,
I don't know.
If you did, I'm proud of you.
Unconventional listening style.
So we answered my question at the top of the show about permanent eclipse. Thanks, Aaron, for that. But now we have a question for Julian. Julian, what was your question this week?
I am also answering a listener-submitted question. This one is from Macks, but Macks.
Oh, cool.
So, yeah, not the normal, like, Maximilian. No, Macks. Macks asks, is there an amount of pineapple that can dissolve a human body? When we pick questions, when we meet and we go through, I got to that one and I was like, that's number one with a bullet. That's easy.
This is the perfect question for this show.
Weird. And as alluded to, I attempted to do a journalism, but we'll get to that. First of all, Macks flexed a little knowledge. This is, something that you see go around the internet, fun facts about pineapple, and Macks clearly has been reading that. Macks added, as we all know, pineapple contains an enzyme that dissolves proteins called bromelain.
Oh, we all know that. Everybody
knows
that.
We all know that. Yeah. Thank you, Macks, for assuming that I knew that, because I totally did. Of course I knew that. It also contains a high level of citric acid. So pineapple quite literally eats you as you eat it. I just wanted to know what amount it would take to fully dissolve a body, if it's even possible. I hope, Macks, that you haven't been waiting on this answer if you need to get rid of a body. Because
Oh, yeah.
Can you imagine he's just sitting next to it and he's just got like tons of pineapple, like canned pineapple, and he's just like waiting for the pod to come out.
At this point, just start carving them up. Not the body. Oh Jesus, no, not the body.
Not the body.
Oh God, the old gods and the new.
It's an interesting question. I think we've all seen some crime dramas where somebody's got to get rid of a body and they put it in a vat of acid or something, right, and decompose it down to some goop and then throw it away, right? Like Breaking Bad, they used hydrofluoric acid or something that.
Yeah.
It's a common trope, right? And it's an interesting question too, because like he mentions, this bromelain, this enzyme in pineapple, when you eat raw, fresh pineapple, you ever notice that your mouth gets all sore if you eat too much of it?
No, I love pineapple.
No?
I eat so much pineapple.
I do too. But like, I remember I was at like a wedding as a kid and they had fruit and I was like, I'm just going to help myself to all the pineapple because I don't care if anybody else wants it because I'm 5 and I have no empathy, you know? And I just ate and ate and ate. And after a while I was like, dang, my mouth is killing me. And it's not just that citric acid. It's that bromelain enzyme that he mentions.
You know what? Now that you mention it, I do have a memory of once having more tummy. My tummy was upset.
You
I
ate
ate
a
a lot
upset?
of pineapple, and then I was like,
no,
poor
thank
baby.
you.
No, thank
Poor
you.
baby.
Yeah, it was uncomfortable.
But yeah, I think it's an interesting point of comparison too if we like compare it to the human stomach.
Okay.
Because as I'm sure we're all aware, the human stomach is acidic, right?
We're all
it's got
aware.
A low pH.
I would say I'm more aware of that than the bromelain.
The bromelain thing. But were you also aware that, you know, your stomach doesn't rely on acid alone to break things down?
It's also mechanical.
Well, yeah, it's like churning and moving the food bolus. This is the term for like the lump of mashed up gross food working its way through your system. Anyway, bolus. Terrible word, right up there with nubile for me. Along with that, right, your stomach physically churning and moving things around and after you've already mashed it all up with your teeth and the acid content of your stomach, you have enzymes in your stomach that are there to further break down food. And the enzyme in your stomach that does that is pepsin, which if you've ever taken like an antacid like Pepsid, you're like, why is it called that? It's because it's, you know, reducing the effect of pepsin. What's really cool, by the way, about how it works is the pepsin in your stomach is actually activated by the acid in your stomach. Like if you're not digesting food currently, then basically the enzyme stays in a shape that doesn't break stuff apart, you know, because you don't want to digest yourself. That would be a waste.
Yeah, I don't want to do that.
But when food comes in, you know, and your stomach gets more acidy, the lowered pH changes the shape of that pepsin enzyme. And now, because the way enzymes work, shape is like everything, you know? So now that enzyme's in the proper shape to go in and start breaking up bonds between the molecules in your food.
All right, break it up, everybody. Break it up.
Break it up. Hey, bolus.
Sorry, Pep. Pep.
Not going to sit here and take this bolus.
Sorry about that, Pep.
So I kind of see a parallel between, you know, the pepsin in your stomach and the stomach acid and the bromelain in pineapple and Macks mentioned the citric acid, right? But it's not that simple.
Oh.
And I did attempt to call an expert. I called up Dr. Shelley Tai. She's a biology professor at my wife's school, and she's brilliant. And I called her up and asked her this question, and she laughed at me.
Of course.
She laughed straight at me over the
like
phone
you do.
and said it was ridiculous. And I was like, well, that's good, because that's the podcast, what we're going for.
Yeah, it's really more absurd, Dr. Tai.
Really. She didn't have an answer for me, and she suggested like that I set up an experiment with pieces of meat and pineapple
at different concentrations.
And I was like, I don't think I have the time for this.
Wow.
But we talked about it a little bit, and you know, I suggested like, how would you make this more acidic? How would you make the bromelain more effective? And she's like, I just don't know. But she doesn't think it'd really be possible. But I dove into it farther, and I think there's a few things that we need just as a general PSA for the world to clear up about acid.
Oh,
things that we call acid.
Thank you for going there, because the basics are complicated.
They are. First of all, Trace, what is an acid?
Whew, isn't it? So acids and bases are two sides of a coin, if you will. And it has to do with your pH level. pH being the power of hydrogen. Basically, how many hydrogen ions are in a solution.
Yes.
More hydrogen ions means more acidic.
Yes, that is
correct. Fewer
hydrogen
ions means less acidic.
Right.
And more basic.
Yes.
Okay. Outside of that, that's already about the end of what I got in my old brain here.
Okay.
But either way, bases and acids are both important, and they can both be caustic.
Correct. Now, you've got the gist of it pretty well figured out. So then the only little logical piece that you're missing is what actually makes an acid, and there are a few different like definitions that as we've come to understand them better, like they've gotten more specific. Yeah. I'm going to use one that's slightly incorrect, an older definition, but it's good enough for our purposes. Okay. And that is a acid is a molecule that is a proton donor.
That makes sense.
So when it's in solution, it lets go of a hydrogen ion, hydrogen being just made up of a proton and an electron. If it's an ion, it's just a free proton floating around in the solution, right? So it's got a positive charge and little bitty hydrogen molecule. And then on the other side of that, a base is a proton acceptor.
I like this analogy. Easy to understand. Even if it's older and maybe not entirely correct, still good.
Yeah, because there's some things that act as acids, but they don't release a proton. And so there's a more technical definition that has to do with like electrons. But to keep it less confusing, we're going to use the slightly inaccurate definition. It's good enough.
It's correct enough.
Yeah. In most cases, especially what we're talking about here, that's going to be
Got it.
So you'll notice a lot of the times acids have names that are like hydrogen sulfide, hydrochloric acid, right? And they're written out like HCl, H2SO4, right? And the H is at the front there because that's what's being released out into your, liquid aqueous solution, and you're dropping the pH. Now, here's the thing. What a lot of people don't understand is acid strength. Like when I say that, do you go to pH right away?
That's the first thing I think of. It's like, oh, that's a pH of 7. It's a pH of 10. It's a pH minus 1.
That's not quite right.
Okay, good.
Because that's more like the concentration of hydrogen ions in the solution, which, by the way, talk about logarithmic scale. That's
man.
Second time we brought up logarithms.
Scale. What are we, Victorian over here? That's a deep science cut.
So acids go on a logarithmic scale, right? And it's a little confusing because, like you said, the lower the number, the more acidic it is. But it's because the formula is like you take that number and you make it a negative, and then you make it the exponent of like 10. And that's the concentration per like liter of liquid. So like something that's pH of 2, that means it's like 10 to the minus 2 of moles of hydrogen, floating around.
Bringing me back to freshman year chemistry. I had to take it twice.
But something that's a pH of 3 is 10 to the minus 3 moles of hydrogen in the solution. So it's literally 10 times less free hydrogen floating around, ripping away at stuff. So that's why it can be a little confusing, but it's math.
Oh, math.
But there's another very important value when we're talking about specific acids, and that's called the Ka value, also known as the dissociation constant.
Whoa.
Right. So Trace, again, what's our definition of an acid?
It's about how much hydrogen ions there are in the thingy.
So an acid is something, it gives up a hydrogen ion.
And then the base is the one that hugs them and says you're okay.
But different acids don't give up their hydrogen ions equally, right? Like a hydrochloric acid and citric acid do not give up, like if you have the same amount of each in like a little vial, the pH of the hydrochloric acid is going to be a lot lower than the pH of the citric acid because the citric acid doesn't always give up its proton.
Got it.
It hangs on to it more. Hydrochloric acid, that gives it up a lot. So that's what the pKa value represents. And the lower it is, the more readily this acid gives up protons until it gets to a certain point where it hits an equilibrium and then, it starts accepting the protons back again. Right?
Yeah.
So
sense.
This is what distinguishes a weak acid from a strong acid. If a strong acid is something that gives up that proton and it doesn't want it back, right? You'd need a ton of free floating protons in the solution before it finally goes, fine, I'll take one back, right? Yeah. So it's a strong acid, and when it lets go of that proton, it turns into a weak base. Now, weak acids are the opposite. They don't give up that proton very often unless there's just not a lot in the water. Unless there's other stuff in the solution that's going to take it off of them. They're like, no, I'll hang on to it. But then if there's a lot of hydrogen floating around in the solution, the base is stronger and the base will take that back. The conjugate base of it. Okay, so I said all that. I know it's a lot.
It's a lot. I'm trying to keep it all in my head.
So here's what's important, and that is that the pKa, that dissociation value constant of citric acid, is actually pretty high.
Oh.
It's not great, right?
Yeah, you want it to be low, as
juice,
a reminder. We want it to be a low number or a low figure. I don't know what the number is, but a low figure means stronger acid.
Right. And then it'll give up more hydrogen, so your pH in your solution will drop lower.
Yeah, which is
Because at a certain pH, it'll just stop giving up those hydrogens. Doesn't matter if you keep pouring more citric acid into a solution, it's not going to make it more acidic after a certain point. Okay, so pineapple juice has a pH of between 3.2 and 4. So it's acidic. Yeah. Citric acid is about 87% of pineapple juice, which is a moderately strong organic acid. So the pKa value for citric acid is 4.71, and the scale goes from like -5 to 50. Okay. Now, your stomach has hydrochloric acid.
Yeah, that's pretty strong.
Do you want to take a guess at the pKa value of hydrochloric acid?
-1, -3, you know.
It's -6.3.
Ooh.
Yeah, the hydrochloric acid in your stomach is really strong.
Yeah.
It wants to get rid of that hydrogen, and it doesn't want it back. It's like a jilted lover.
I was going to say,
get out of my house.
There's a lot of relationship drama in these acids and bases. Jeez.
So because of that, the pH level in your stomach is 1.5 to 2.
Okay. Whoa.
So it's really acidic, right? To put that in context, if our pineapple juice has a pH of 4 and our stomach acid has a pH of 1.5, because of logarithmic math, that actually means your stomach acid has 310 times the free-floating hydrogen atoms that are ripping stuff apart and messing with stuff, right? So that's why stomach acid is effective at breaking down the stuff you eat, along with that pepsin enzyme that gets activated at those very low pHs, which is cutting stuff up. That all make sense so far?
Yeah, I think so.
So the problem with pineapples and pineapple juice is this bromelain, which, it does cut up proteins, right? It gets in there, it breaks the peptide bonds. It's most effective at a pH of like 6 to 7. So like almost neutral. Yeah. And if it gets more acidic, it doesn't work as well. So you lose that like protein breaking component that's pretty essential to actually breaking down like organic material, proteins and stuff.
But, okay.
So it still can do something at the pH of pineapple juice, but it's just not as effective. And if we want more acidic, which we do.
Yeah, if we're trying to dissolve a body, we need a lot of strong, ripping, jilted hydrogens.
Yeah, that bromelaine's not going to be as effective, and then the acid itself is 310 times less acidy than like hydrochloric acid. And I actually found, to put things in context, I found a thesis from a student at Boston University that used pigs in acid to like kind of see how, I know it's gruesome, but they wanted to see how long it would take if you were like a murderer and you wanted to dissolve a body. And hydrochloric acid, the stuff in your stomach, they used like 31% hydrochloric acid, and they put pig tissue in it. It failed to dissolve soft tissues. It destroyed bones within 68 hours, but it didn't break down the soft tissue.
You'd think the other way around.
Well, but that soft tissue, you'll remember, is held together by these bonds, these peptide bonds. Then that's why you need something like pepsin to break that part of it down, right?
Yeah.
To actually get in there and slice those bonds. But your bones, which are like,
calcium
ions, if you've got these hydrogen ions floating around, I can see how that would break down the structure of your bones. They increase the heat to 40 degrees Celsius. The soft tissue's still not entirely dissolved, but all the bones were destroyed in 24 hours.
Oh, wow.
They did this with sulfuric acid, which is H2SO4, which has a pK of like -3, but they did 93% sulfuric acid. So like a really low pH. That destroyed all soft tissue within 52 hours. But the bones took longer. The bones took 28 days.
Oh, wow.
With sulfuric acid. Yeah. At 40 degrees Celsius, all the soft tissue was gone in 2 3/4 hours. All the bones in 9 days. At 100 degrees Celsius with sulfuric acid, it took 3/4 of an hour, so 45 minutes to destroy the soft tissues, and all the bones were gone in 9 hours.
Whoa.
So if you're going to use acid to get rid of a body, pineapple juice, if you kept refreshing it to keep bringing in new hydrogen ions, like maybe, and bromelain, but like you'd need, by my count,
really
at least
have a lot of time.
310 times the volume of citric acid.
What you're saying is, if you say own a pineapple juice making company, and since you're a murderer who's dissolving a body, already have low morals, and you leave the body somewhere along the process of from the juice making into the vat that you would then ship it out through, somewhere along that process. So it was just constantly being bathed in fresh, new juice.
Right.
It still would take many hours to many days.
Days. I mean, we're assuming that's going to break up the soft tissue.
Also, you'd have to keep it very hot in there.
They use pineapple juice to tenderize meat, right? That bromelain is good at breaking up specifically collagen. Collagen is like the connective protein between a lot of our tissues. It's the most common protein in our body. It's like 30% of the proteins in our body are just collagen. Nice. So it could do that. It could tenderize us a bit, but you might not break up other soft tissues that are held together with collagen. Yeah, and it would take an enormous volume of constantly refreshed pineapple juice. Could you do it? I'm going to tentatively say yes.
If you had unlimited time and unlimited pineapple juice?
It would be inefficient. You could go the other way, though. You could use a very strong base like lye.
Great. Excellent choice.
And yes, that is a common body, soft tissue destroying compound.
Yeah. When I worked at the museum, we learned a lot about lye because it used to be impossible for the human body to digest corn. We usually eat like sweet corn, which is a specific and bred specifically to be eaten. But indigenous tribes of the North American continent didn't always have that. Like that was a specific breed that was created to be sweet corn. But before that, you'd have to take the corn kernels and cover them in lye to destroy the outer cellulose before you could eat it. And then you'd have to wash it real good because if you didn't...
Jeez.
Yeah. If you didn't, you'd be in big trouble.
That's nuts. Yeah. So lye is sodium hydroxide, NaOH. So when that breaks apart in liquid, you've got Na, just like how when you put salt in, right, it breaks up into Na and Cl. You've got Na plus and then OH minus. Mm-hmm. So OH minus, what do you think that's going to do?
It's going to mess things up.
Yeah, by taking protons, right? That's a great proton acceptor. It turns into H2O. So it's a very, very, very strong base, and that will also break apart tissues and stuff. As a matter of fact, it's funny, just earlier today, I was on a little, soap making operation, and they had some soap on the counter, and I was like, it was just sitting off to the side, and I was like, hey, can I get a bar of soap to take home? And they were like, oh, you don't want that, it's curing. And I was like, what do you mean? And they're like, yeah, the lye in it is still active, and if you bathe with it, it'll burn your skin.
That's the other thing they use lye for in old world America is they would use it, mix it with animal fat, and then turn it into...
Yeah, so that would be more than an acid, definitely more than pineapple juice. You would want to probably use sodium hydroxide, which you could get because it's got all sorts of industrial uses. I'm not saying don't do it, but like Macks.
Just buy a pineapple juice factory.
Start a pineapple empire, and when you facilitate a coup that overthrows the government and need to get rid of the dissenters,
just throw them into the waterfall, Willy Wonka style.
Yeah, liquidly bathe them. So no, I think a lot of the, pineapple eats you back, bromelain and the acid, I think a lot of that's kind of overhyped on the internet. Does it break down some tissue? Yeah.
The super soft, very sensitive tissue of your mouth.
In your mouth, exactly.
Which is not supposed to be, you're supposed to put things in your mouth that are edible.
Which, by the way, bromelain, it's honestly, the pineapple plant probably wants it to do probably just that amount of damage. I mean, it doesn't want, it's a plant, but you know what I mean. Plants in the pineapple family, they make bromelain, but they make it mostly in their stems, the part of the plant that's not a fruit that's going to get the plant anything if an animal comes and eats it. So the bromelain concentrations are higher there. If an animal comes along and nibbles on the stalk, it's like, that hurts. But if it eats the sweet, tasty fruit, especially the bromelain concentration's highest in the core of the pineapple. So if it eats the outside where the seeds are, that's great, but the pineapple fruit tree is like, no, hey, don't eat the rest of me. That's off limits, which I thought was kind of cool.
From an evolutionary perspective, the pineapple seeds I just looked it up, are typically less than an inch, about 3/8 of an inch from the outside edge in freedom units. In centimeters, that's 1 centimeter. So if you can get to that then you've eaten the seeds, which if you're an evolved fruit, that's your goal, is to have some animal come and eat. You wouldn't want to digest the animal that is eating your seeds to spread them around.
Yeah.
That doesn't seem like a good evolutionary system, really.
Yeah. You want to entice it, eat the fruit, but
don't
eat
eat the
meat.
stems, because I need those to grow
I'm
more
off
food.
the menu.
More fruit.
Yeah, exactly.
Very interesting.
Macks, I hope that was satisfying. Maybe I'll take Dr. Ty's advice and I'll go and put some meat in a bunch of pineapple juice. I bet it'd get moldy and gross
Katie
first.
is out of town.
I've got free reign of the kitchen.
You want, buddy.
But yeah, as far as I know, like, maybe, but it'd probably be a huge waste of time.
There are
and
better
pineapples.
substances than pineapples that would probably not cause flags any more than buying 1,000 pineapples a week just to juice them.
You know, you could do it once, and then when the news gets out, when you inevitably get caught and get branded like the pineapple killer, you know, then everybody's going to know, and they're going to be on the lookout for the dude with a shopping cart just full of pineapples. Oh, by the way, a lot of prepared, like canned pineapple and stuff, it's heated before it's canned, and that denatures that bromelain and renders it useless. So you want the fresh stuff.
If you're going to digest a body and or other.
Yeah, if you're going to go through with this absurd, heinous scheme. Yeah, you need the fresh pineapples. So just a cart full of pineapples.
Watch out for that. If you see that at the store, be afraid of that person.
If you see that, murderer, guarantee, or luau host preparing for his party. Those are the two options. There's nothing in between. So maybe you want to be invited, but maybe you're like, ugh.
Are they? Look for other signs. Are they wearing an aloha shirt?
Hey.
Does it look like they wear aloha shirts a lot, or is this a costume that they're only putting on?
Aloha shirts, great for hiding bloodstains in that pattern, you know? It's hard to kind of tell, like, what's a flower and what's a blotch of blood. Who knows?
That parrot sitting on the tree on their shoulder sees all.
Hey, you want to come over for a cookout? I don't know. Am I on the menu? What are we doing?
Oh my gosh, that's great. Well, thanks, Macks, for asking that question, and Aaron for asking your question. Again, we could not do this podcast without our listeners asking these questions, so we really, really, really appreciate it. Thank you for sending those in. If you have an absurd question you want to ask, go to that'sabsurdshow.com. You can listen to episodes, you can read little blurbs about each episode, and you can even, of course, ask us a question. You can also, subscribe there if you haven't already followed us on iTunes or Spotify or wherever it is that you're listening. If you haven't left us a review, please leave us a review. That's how people know that the podcast is good. You might know that because you've already listened to a whole episode. Tell other people that it's good, because when you go and listen to a new podcast, the first thing you do is say, like, what's it rated? Is this worth my time?
Yeah.
So tell other people it's worth their time.
Somebody recently said that they're recommending it to their friends and family in person. And also, I mean, this doesn't help with data or anything, but it made me feel really good inside, and I appreciated that.
Yeah.
So thank you.
I love it when people reach out and they tell us how much they like it. We really love that. Before we wrap, we're close to 1 year since we announced the podcast. This is, again, coming out on April 4th. We announced the podcast on April 1st, 2023. I'm just so pleased as punch to be able to tell you to go and look at every title of the show. Just scroll
see
through
if you catch anything.
the titles of the show in order and see if you notice anything. And if you do, shoot us an email at hello@that'sabsurdshow.com and we'll send you a sticker, the first person. Say the first
sticker.
2 or 3 people who send us an email. But anyway, thank you for listening. This episode was written, created, and produced by me, Trace Dominguez.
And me, Julian Huguet.
And it was produced and edited by the wonderful and fantastically talented Kyle Sisk.
Special thanks to listeners who submitted questions featured in this episode, Aaron and Macks. If you'd like to submit a question, look for the form in the show notes. You could also email us at hello@that'sabsurdshow.com or visit that'sabsurdshow.com/ask. We love getting these questions. We get a big kick out of them, and they're what makes the show run. So send them in.
And remember,
be wary of people with too many pineapples.
Be wary the pineapple man.
Beware the pineapple man.